Today's lecture is on limits. It's the first of a series of lectures we're going to do this week over limits, and I wanted to review first. So let's talk again about what is a limit and take a look at some notation. So here's the notation for a limit. So we write the limit as x goes to a of f of x. And so let me write down how you say this. So this is said the limit as x goes to a of f of x. And if it exists, let's say it's equal to some number L. So is equal to L. I always like to write down how you say things like this, because then you can kind of see, okay, here's the limit. So that's why we say the limit. And then as x goes to a, that's what that means, as x goes to a. And of course, of f of x, so here's my f of x. And then is equal to, of course, there's the equal to, and then we can put a box around L. Now what this means, so what does this mean? So what's the meaning of it? So really, when I see this limit, if I see a limit, let's say as x goes to, let's do 5 of f of x. I'm going to use the picture above here. What this is saying, it's asking a question. It's saying as x gets closer and closer to 5, where does the value of the function go? What does it get closer and closer to? So as x gets closer to 5, what happens, what happens to f of x? All right, so what this means is, what does f of x get closer to? If anything, if anything, because it may not exist. We've talked a little bit about this. So let's take a look at this picture above, because we've already done this problem. But as x gets closer and closer to 5, so here's 5 right here. So as you get closer and closer to 5, you notice from the left the function goes to 4, and from the right the function also goes to 4. So the idea is that the limit is equal to 4, even though the actual value in this picture, I think, is supposed to be right here. So even though the actual value is supposed to be 1. I didn't copy that little circle there. We can look at another limit that doesn't exist. So the limit as x goes to 1 of f of x. And so if you look at this limit, you come in from the left-hand side of 1, and it reaches 2. And so we can write this down as, so more notation, this is the left-hand limit. So the limit as x goes to 1 from the left of the function, f of x, is equal to height 2. And I always remember this negative sign means from the left, because it's kind of like from the negative side of the number. So if you think of a number line, here's 0, the negative numbers are over here, the positive. So when you're coming in from the left, you're coming in from sort of like the negative side of numbers. Whereas when you're coming in from the right, this little plus sign means coming in from the right, coming in from the plus side, the positive sides of numbers of f of x. You look up in the graph, and as you come in from the right, you can see you approach height 3. And because these limits are different, from the left it's 2 and from the right it's 3, we say this limit does not exist. So D and E, which again means does not exist. I once had a teacher explain to me the idea of a limit is sort of like the best guess to the value of the function without looking at the actual point. So like the limit here is actually 4, even though the actual height's supposed to be 1. Whereas the limit over here as you go to 1 doesn't exist because your best guess from the left would be 2, your best guess from the right would be 3. Since 2 is not equal to 3, you don't really have a best guess. So that should review some notation and left-handed versus right-hand limits. We talked about the graph last time. Now I want to start talking about how we do limits with formulas. So let's start with some examples. And so I have 4 examples here. That should be D. And the idea is, the first thing you want to do is just try to plug into the point, because remember, if a function is continuous, we have this definition, the limit as x goes to a of f of x, you simply plug in the point if it's continuous. And a lot of the functions we deal with are continuous, so the first idea we have is typically plug in the point, plug in this case 3 into the function and see what you get out. So that's going to be equal to, and I have negative 2 times 3 squared plus 3 times 3 minus 1, which is equal to, and just multiply it out, so you have negative 2 times 9, which is negative 18, plus 9 minus 1, which is equal to a negative 9 minus 1, which equals negative 10. Negative 10 is a perfectly good number, so that's actually my answer. In part B, you're going to get something a little bit different out. So in part B, when you plug in 5, you're going to get 5 squared minus 9 times 5 plus 20, all divided by 5 squared minus 25. And you can see on the bottom you're going to get 0. And if you look at the top, you'll see here you're also going to get 0. So you're going to get what's called 0 over 0, or indeterminate form. So I put quotes around these because they're not really numbers. You can't even, they're not really defined. So it's more of me thinking. So these are called indeterminate form. That's what 0 over 0 is called. The idea is you cannot determine the limit as given. Both of these expressions, the numerator and the denominator, are going to 0. And the question becomes, how are they going to 0? Are they going to 0 in a similar manner, meaning somehow they may cross off and 0 over 0 may actually give you a number? Is the bottom going to 0 faster, or is the top going to 0 faster? Because these will change the outcome. I always it's sort of simple to understand. I always tell students that, okay, it's sort of like my income. My wife and our income is sort of going towards 0, but mine's going twice as fast. So if you take the ratio of my wife to my income and mine's going twice as fast, you're actually going to get a half, because mine is going to 0 more quickly. So just think about that idea. And what we can do here, though, is we can do some algebra. So I'm going to rewrite this down here. Limit as x goes to 5, x squared minus 9x plus 20, all over x squared minus 25. So we can do a little factoring here, top and bottom, and you're going to see things are going to cancel. So whenever I see a quadratic anyways, I'm kind of trained to factor it. So you can factor the top, so you're going to get x minus 5 times x minus 4. And you can factor the bottom, so x squared minus 25 is x minus 5, then times x plus 5. And what happens is that these x minus 5s are going to cancel. And notice when you cancel them and you plug in 5 again, you're no longer going to get 0 over 0 because you canceled off the part of the expression that gave you 0 on top and 0 on bottom. So now I have the limit as x goes to 5 of x minus 4 over x plus 5. And I'm going to plug in 5, so I have 5 minus 4 over 5 plus 5, which is equal to 1/10. So 1/10 is my answer. It's important to show all the steps, so I know that you're actually thinking properly. There's certainly ways to check this, which we'll talk about this answer, which I'll talk about in a little bit. But let's look at the next one. So part C. So on part C, the idea is I plug in 2, and I get 1 over 2 minus 2. Now this is me thinking because I just noticed that in the bottom I'm going to get 1 over 0. And so this is not an indeterminate form. When you have a number over 0, it just means the limit does not exist. And if you think about the graph of this, you'll see that at 2 you're going to have a vertical asymptote. And if you graph it, basically what's going to happen is you'll see from the right-hand side you're going to go off towards infinity, whereas from the left-hand side you're going to go off towards negative infinity. And so obviously the limit cannot exist there. So we write D and E does not exist. And the last one, part D, I'm going to copy it. Well, let me plug in the point first. So when you plug in 0, you get e to the 3 times 0 minus 1 all over 0. I immediately know that I have to start thinking here. So now I'm thinking and saying, okay, well, you can't divide by 0. And on top, you're going to have basically e to the 3 times 0 is e to the 0, which is 1. So you're going to have 1 minus 1 on top over 0. Oh, and that's a 0 over 0 form. And again, what that means is that you have this indeterminate form. So you cannot determine the limit as it is given. So there are several things that you can do here. For us, what we're going to do is we're just going to make a table. So we're going to have our x's over here, and we'll have our outputs, e to the 3x minus 1. That should be down there. Now let me erase that so it's clear. So e to the 3x minus 1, all divided by x. And we're just going to simply plug in numbers close to where x is approaching, so close to 0. So you can plug in a number like, let's say 0.001, and let's see what happens. So we have a calculator, so we want to use our calculator to do this, because to do it by hand, it wouldn't just take forever. I don't know if we could actually do it by hand with what we know right now. So, of course, we use our calculator. And so we have the left parenthesis, second ln. We have 3 times 0.001. And then we're going to take off 1. So I'm just plugging this number in here. So I have e to the 3 times 0.001 minus 1. And then I'm going to divide that all by 0.001. I'm basically seeing what happens as I approach from the right of 0. So in parentheses, all divided by 0.001. I hit enter, and I get out this number, about 3.0045. So about 3.0045. Now, if I had to guess, I'd probably guess this answer is 3, because I'm assuming that it's going to be a nice, the limit's going to be a nice answer. But let's check it out from the left, too. So let's do the same number, except let's take it negative now. So we're approaching 0 from the left, basically. And what do I get out? So I plug it into my formula here. So e to the 3 times negative 0.001, and then minus 1. And then this is all divided by 0.001 with a negative sign. And again, I'm going to put this into my calculator and try to speed things up. I'll just hit second entry, and then I'll insert a negative sign here, and I'll go up here and insert a negative sign here, and I get out 2.9955. So 55. So from the right, it looks like it's approaching 3. From the left, it's approaching 3. So my guess in part D, so this implies that the limit as x goes to 0 of e to the 3x minus 1 over x is actually equal to 3. And I can test this further by, adding more zeros to my 0.001 if you want. So I could do, let's add 2 more zeros. And so come down here and add 2 more zeros. So I'm even closer to 0 now. And hit enter, and I get 2.999. So it's just going to get closer. As I get closer and closer to 0, Right, remember what the limits is actually asking a question. As I get closer and closer to 0, this expression right here, this function, gets closer and closer to 3. Now, like I said in part B, I mentioned that you can actually test your work. So to test your work, we found that this answer was what? 1/10? We found it to be 1/10. So if I want to test my answer, I can take a number really close to 5, like 4.999, and see if I get out about 1/10. So let's check it, just to check our work. So like 4.999, and I'm going to square it, and then I'm going to take away 9 times 4.999, and then plus 20, in parentheses, divided by left parentheses 4.999 squared minus 25. And if I did everything right, I should get out something close to 0.1. And I do, 0.099909991, which is close to 0.1 if you round up. And as I get closer to 5, I should get closer to 1/10. So you can always check your work on these things. All right, let's look at the next problem. So we want to work with some left-hand and right-hand limits. So we want to use the left-hand and right-hand limits to determine what this limit's equal to. So let's take a look. So we'll take a look at the limit as x goes to 6 from the left-hand side. So you're coming in from like the negative number side. And I have my function f of x, which is equal to the limit as x goes to 6 from the left-hand side. Now, realize when you're coming in to 6 from the left-hand side, so I'm coming in from the left over here, all my numbers, all my x values are less than 6. So take a look at the formula here and try to figure out which one would you use, the top or the bottom, if you're coming in from the left-hand side. And you want to use numbers that are obviously less than 6 because you're coming in from the left-hand side, and you say, oh, I use the top. And so I'm going to use x minus 1, which is equal to, and of course the idea is just plug in the number and see if it makes sense. So let's plug in 6, and so I get 6 minus 1, which equals 5, which makes perfect sense. So that's my left-hand limit, where my right-hand limit, as x, the limit as x goes to 6 from the right-hand side of my function, it's going to equal the limit as x goes to 6 from the right-hand side. And on this one, when you're coming in from the right-hand side, my x values are greater than 6. So of course you're going to use the bottom one. And so this is then x squared minus 2x. And you simply plug in the point. So plug in 6, so you get 6 squared minus 2 times 6, which is a 36 minus 12, which is equal to 24. So here's my left-hand limit, here's my right-hand limit, and so therefore I'm going to conclude, so therefore the limit as x goes to 6 of f of x, well, my best guess from the left-hand side is 5, my best guess from the right is 24. They don't agree, so I say this does not exist. And I can even say why, since 5 is not equal to 24. That is the limits, right? The limit from the left-hand side of 6 does not equal the limit from the right-hand side of 6. All right, so what have we done? We've done a bit, okay? We talked about a little bit what a limit is. It's sort of like this best guess to the value of a function without actually looking at the actual point. You look around it. We talked about notation and left-hand and right-hand limits. We talked about graph in the previous, how do you do a limit with a graph in the previous video. In this one, we did formulas. And finally, I want to end with the actual definition of a limit, because this is someplace where students really struggle, and it has to do with this sort of quantitative literacy aspect of this course, which is trying to understand what something is saying in mathematical terms. So here's the definition of a limit, and I'm not going to test you on this. This is more of just something I want to expose you to And so you can start to get a feel for how you read sort of technical writing. So we say that the limit of f of x as x of f let's restart. We say that the limit of f of x as x approaches a is L, and we write this, the limit as x goes to a, f of x equals L, if you give me any number, so for every epsilon greater than 0, there's going to exist a delta greater than 0 such that if this is true, then this is true. So what you need to notice here, and what's important, and you may not have thought about before, but absolute value is really a distance function. It's just saying, hey, the distance from x to a is going to be less than some number, will then imply that the distance from the value from the function from L is going to be less than epsilon. And there's a picture down here, and this is what really the definition of a limit actually is. And remember, so what we're doing here is I'm actually trying to teach you how an engine of calculus actually works, because what limits are is they're sort of the engine of calculus. And you can drive calculus, you can do calculus without understanding how the engine actually works. But I find it, from an aesthetic point of view, more enjoyable to actually understand how it sort of works. And it's not terribly difficult. There is a lot of value in trying to go from here to this picture, and certainly from this picture back up to here. So all this stuff right here is really saying this picture. It's saying, hey, if you give me an epsilon, you give me some number, and we're going to do an example in a minute, but if you give me some number, what you can do is you can find a delta down here, such that if your x lies between x minus delta and a minus delta and a plus delta, then I know the value, the height of my function, will be within my sort of region up here. All right, so this is what you're given. You're given epsilon, and you want to say that you can find some delta, so you always lie within this sort of green region. So let's do an example, and maybe this will make a little bit more sense. Like I said, this is really sort of tough, and I don't test students on this. It's more of I just want to expose you to it so you get a feel for what this stuff actually means. So we want to use the definition of the limit to prove that the limit as x goes to 5 of 2x is equal to 10. And so here it says for every epsilon, so I'm going to let epsilon greater than 0 be given. So let epsilon greater than 0 be given. So it's some number bigger than 0, so it could be, I don't know, it could be 2, it could be 1/2, it could be 1 over 1,437,562. Just some number greater than 0. And let's put a comma here, and then take delta to equal. Now you get to pick what delta is going to be, and here you have to pick it to be a certain quantity, dependent usually on epsilon. So I'm going to choose it to be epsilon over 2, and you'll see why in a minute. Right? So take delta to equal epsilon over 2. And I want to prove, again, I'm trying to prove why this is true. Now I know if you plug in 5, you get out 10, so we already know that. But using the definition, I want to show why this is actually equal to 10. So it says, if you have this, and so I'm just going to copy that down. It says, if we have 0 less than the absolute value of x minus, now my a, here's their a, is different. My a is 5. So x minus 5 less than, and then they have delta here, so less than delta. Then they have, and I'm going to make a little more room down here because mine's going to be a little bit longer than theirs. Then what do we have? We have then f of x, which of course I can write down instead of, here's their f of x. Okay, my f of x is a 2x, so I'll write down 2x minus, and of course they have L here, which corresponds here, so my L is 10, so 2x minus 10. And I want to show that this is going to be less than epsilon. So notice this is equal to, well, I can factor out a 2, so that's 2 times x minus 5. And now since this is the absolute value, I can just pull out the 2, so this is 2 times the absolute value of x minus 5. And again, I'm trying to show this is less than epsilon. Now x minus 5 I know is less than delta, so I know this is less than 2 times delta, which is actually equal to, so notice, I know delta is equal to epsilon over 2, so this is actually equal to 2 times epsilon over 2, and so the 2's are going to cancel, and I'm going to get back epsilon. which is exactly what I wanted. So now I know that if I have this, just like up here, I have this, then I have this. The absolute value of 2x minus 10 is less than epsilon, just like over here. So my conclusion is, therefore, the limit as x goes to 5 of 2x is equal to 10 by the definition of the limit. So what the limit is really saying, if you go back up, and let's just look at this picture real quickly. All right, so look at this picture right here. So basically what the limit says is you have some control over the function. So if you give me some epsilon bigger than 0, and I look at values that are a little bit bigger than L and a little bit smaller than L, then I can find an interval down here where I can control all the possible outputs. I can make sure that they're actually within this sort of green region. So basically you can control the function.